Up next, we will have Dr. Nick Fye. Dr. Fye is an associate professor at the University of Texas at Austin, appointed as a core faculty within the Walker Department of Mechanical Engineering and Texas Robotics Center of Excellence. He also holds affiliated appointments with the UT Southwestern Medical Center and UT Austin Dell Medical School. After attending college at the University of Texas at Austin, graduating in 2006, 2008, and 2011 with bachelor's, master's, and doctorate degrees in mechanical engineering, respectively, he pursued research in the Center for Bionic Medicine at the Shirley Ryan Ability Lab, formerly the Rehabilitation Institute of Chicago, and Northwestern University's Feinberg School of Medicine. As the director of the Systems for Augmenting Human Mechanics Laboratory, his research focuses on the intersection between rehabilitation robotics and neuromuscular biomechanical engineering and applies these technical domains to inform the design, control, and assessment of prosthetic and orthotic technologies. Typically, his research focuses on diverse and transient forms of human ambulation and the extent to which next-generation lower limb assistive technologies and clinical interventions enhance human ability. Support for his research has been provided by the U.S. Department of Defense, the NHS, and the NSF's National Robotics Initiative. Please join me in welcoming Dr. Nick Fye.
All right, thank you all for coming. Thank you for the invitation by the organizers of the symposium. It's always great to be here and describe some of our research in the lab that's done by students, not necessarily faculty, and especially if they're here. And so, yeah, so I'm in engineering and robotics. Our lab is called the Systems for Augmenting Human Mechanics Lab. Our main pursuit is to restore human mobility, and our kind of core knowledge would be this sort of holistic perspective on how human motion is derived, how it's caused by the nervous and muscular systems, how to interfere or assist in that movement, and then various ways of defining human performance. You can imagine that's similar but also different from autonomous systems. So this is a project on this slide here. It's almost exactly 10 years ago. This was my first introduction to robotics as a research project. I was at a rehabilitation hospital in downtown Chicago. Part of the hospital fundraiser was to enable this person with a knee disarticulation amputation to climb the stairwell of the Sears Tower. It gained a ton of attraction. Morning news shows picked it up. Down here in Texas, I'm from the San Antonio area. My aunt texted my mom, texted my grandma. Why is Nicholas in a stairwell in Chicago? His hat's backwards. What's going on? Basically, we had a lot of hospital swag on. I had a backpack with an extra robotic leg, lots of batteries, and I was sort of the play caller of that whole experiment. Had a sleeve with a key fob. Should we get in trouble with this? And so this was 10 years ago. Much like the keynote, things change, but not that many things change, right? In human mobility research, more of the real-world scenario would be this one. So this is part of a group that I helped start in Dallas-Fort Worth called the Adaptive Sports Coalition. This is actually a Paralympic athlete on crutches, not because he needs crutches. He's playing amputee soccer, where the rules of the game are you have to use crutches. You cannot kick the ball with your amputated limb. And some of this is around leveling the playing field, of course, right? People can have more expensive prostheses, taller prostheses for running quicker, shorter prostheses for being more agile. But I would argue that a lot of this has to do with limiting factors of the technology. So you think about this problem in robotics. We deal with wearable robots, like prosthetic legs. There's a lot to ask of a intelligent system. From simply holding on to the limb, that's very difficult, non-trivial thing to do, to recognize human intention. But even after you've done that, to render a biomechanics-aware response that's somehow well perceived by the person wearing it. And ideally, that is a continuous process, right? The system learns about the person, and of course, this is environment dependent. A lot of those same principles are shared in other domains, other types of people with mobility deficits, or even without deficits. Able-bodied individuals injure themselves through repetitive use. They also have energy limitations, right? You'd all like to exercise longer, potentially, when you're on a ski trip. You'd all like to be more confident in downtown Chicago when there's ice on the sidewalks, or Texas maybe because there's salt everywhere in Chicago. And so this is a few of the patient populations we've studied, and you can sort of define certain problem statements similarly to the one I did before. So it's not surprising then that we have experience with different domains or different types of devices, from robotic leg prostheses. These are newer versions. If I can find my mouse here, maybe I can use, I have a mouse. Motorized knee and ankle prostheses. These are sort of capitalizing on advancements actually in the drone industry. So this is an open device that's using pancake motors that are T-motors that are typically used in drones. The designs are fully open now, though it's hard to build them and maintain them, of course. An exoskeleton device in the middle. I brought this one up because it was actually, the initial market was to help people to downhill ski longer. So it's an exoskeleton that's pneumatically controlled as opposed to motorized, and it's only unidirectional, so it's only providing any extension torque. So this company out of on the West Coast called Robotics developed it and is now looking at musculoskeletal applications of it. And then you have on the far right, of course, something that looks a lot like a stretchy rubber band, where very simple, very form-fitting, and thus has very form-dependent properties of the human. So in these types of projects, we look to kind of configure and embed a lot of physical intelligence within where these devices are placed, their passive properties. We characterize a person's motion and mobility deficit and things like that. So some of the problems that keep us up at night, at least myself, not necessarily the students in the lab, or maybe they do, is that we study typically mobility impaired individuals. So you have this controller hierarchy we've described. Lots of people describe it: a high-level controller, a mid-level controller, even a low-level actuation level controller. And if you're studying people with mobility deficits, you don't really want to have them walk that long, right? But yet you're trying to intervene in their gait pattern. And so some of the things that we target are how we can improve this configuration. How can we have these devices learn about people and to put the right device or the right controller on specific people? That's challenged by the fact that people are hard to study. Even, of course, autonomous robots are hard to study as well, but you can obviously sensorize autonomous systems, maybe more so than humans, though a lot of consumer products like smartwatches, smartphones, even footwear. Nike came up with a smart basketball shoe maybe over a decade ago. It's supposed to help you understand how high you were jumping and some differences in how you were playing basketball. That hasn't really caught on along the theme of the keynote. And so really, how do you probe and ultimately develop policy around a wearable robot is limited by the information you can extract about a person. And then the third major challenge is as devices get less obtrusive, more form-fitting, embedded within your even clothing, socks, compression wear, things like exosuits, the human form and its motion are really specific. It's almost as unique as your handwriting, right? The way that we walk in an environment, if it's a family member, you don't even need to see their face. You can probably tell who that is. And so a person's motion is as specific as they are. And so we want to be able to account for that. So with the remaining time that I have, I'm going to zoom through a couple highlights of this. So one of the major thrusts of the lab for the last few years has been to look at very new levels of sensing. So electromyography is a very traditional electrophysiologic signal. We're using ultrasound as a measure of muscle tension. And in this case, this is a sort of a snapshot of quadriceps sonomyography, imaging across 3 of your quadriceps as people are walking on a treadmill. And so you have this repetitive change in the the image rather. You can pull features from this, and it's really associated with an increase and decrease in muscle tension. Muscular tendon tension, of course, is shared between tendon and muscle. So you can get a lot of information about this. And we've done things like using machine learning, predict future trajectories of joint torque or joint position. So ambulation cyclic, so you have some time, you sort of know what's coming up, right? As soon as the foot leaves the ground, you know that there's a swing phase. You can store information, predict subsequent behavior. So we've done that across various terrains. We've also predicted the physical interaction you would have with the ground and the torque requirements then that your joints would undergo there. A lot of issues of practicality we've gone after by showing that we can embed this inside of prosthetic sockets with very small miniaturized versions of ultrasound. This is, again, using more of a machine learning-based method to predict motion. And beyond that, now that we think we understand quite a bit about the signal and the type of application of it, we're going a little bit away from machine learning AI and throwing more formal methods at it to extract stereotypical patterns of movement and torque generation during widely varying activities. Second example is more around the objectives that we would like to optimize for. So we have some students on campus right now, Finn and Ariana, working on projects funded by the DoD. Nathan was a postdoc in our lab a few years ago. And one of the things that a lot of people focus on for mobility, same with humanoids, is energy consumption, right? We had one of the final slides was passive dynamics, right? Which is an energy-free form of locomotion. That's not what humans do. It's not really what humanoids do, but you can try to capture some of those features. But imbalance is harder to quantify. And specifically, we focus on angular momentum as a time-varying signal. That's a very difficult thing to do. I'm going to move forward here. Traditionally, in biomechanical research, you would have an optical motion capture system. You would put lots of markers on a person, maybe around 50 or 60, define an inertial model of a person, and capture directly from physics-based relationships the imbalance of someone. We've gone more towards machine learning AI, more from a practicality perspective, and in the sense of we can sort of have very sparse amounts of information, maybe only 5 mechanical sensors on the body, and predict over continuous terrain someone's balance. In addition to that, you can sort of imagine a different objective, right? So in the case of a person who's wearing an assistive technology on one limb and using their biological limb for the other, in the case of limb loss, they typically develop joint diseases like osteoarthritis, osteoporosis. So we can also try to predict, for example, ground truth physical interaction with the ground from newer versions of smart insoles. And we're doing this inside of the robotics building in HT there. I don't know how much time I have for this one, so maybe I'll move through it. But the point is that if you're trying to have a device or a person learn to use a device better, maybe they've already sort of optimized their behavior for something. And we know that we can model that in biomechanical engineering. Newer forms of modeling are called predictive simulations, where instead of trying to explain what's happening, in the case of the left image, that's an unexpected 45-degree cut, we can show what could happen if you overlaid a performance-based objective like reducing your imbalance. And so we can do this during transient changes of direction. We can do this during even level ground walking. This is the same person being pushed towards a balanced optimal gait, an efficient optimal gait, and an effort optimal gait. And specific people do this in different ways. So I'm going to move through these videos real quick without crashing the computer here. So these are 5 different people, all with an efficient gait, starting with their known walking mechanics. And let me get to the end here. There we go. All right, so I know my time's up. I'm going to sort of highlight sort of the last extreme, which is a very sort of physically intelligent device, one that's not sensorized and actuated. So we have some work that seems to be getting interest from Ottobock and Hanger in sort of these soft stretchable exosuits. And for this, we really approach a sim-to-real type of application where we model the human motion, its dynamic shape, and we search for what are the optimal configurations of these types of systems to, in this case, reshape the energy distribution within the person. This is showing an MS type of gait pathology. So I'll stop there. Thank you.